We're going to start off by doing a couple of multiple choice questions. This one, number 3, appears on page 11 of your worksheet booklet that I gave you yesterday. You can look in that worksheet booklet, or you can have a look up here and answer this question. I'll give you about 60 seconds to work through it and see if you can come up with an answer A, B, C, or D for that, and then we'll take a look at it as a group. All right, you've had a chance to work on this now. What jumps out at you in this question? Forget about the numbers. We talk about that a lot, right? We're looking at givens. Those are important, but they're not the most important thing. Even in this question, that question that I always ask you, what's really going on in this? That's kind of secondary right now. What jumps out at you right now before we even think about what's going on or before we think about our givens? Is there anything that jumps out at you as being worthy of circling with a red pen here? Drawing attention to so that I don't forget to deal with it later on. I got kilometers per hour. I definitely want to be in meters per second here. Was there anything else, Ilma? Yeah, the milliseconds, both of those. Now we can start thinking about what's going on in this question here. It says, in an automobile collision, the severity of injury can be reduced by an airbag. We talked about that a little bit yesterday, right? The idea of a predetermined impulse, reducing, increasing the stopping time with an airbag, reducing the force. The car is traveling at 100 kilometers per hour, stops the driver, 62 kilogram driver in 90 milliseconds. What's the average force? Where are we going with this question? What concept applies in this question? There's 2 words that lead me to that concept. Yep. Yeah, there's a force and a time. Here's a force. Here's a time of 90 milliseconds. When I see a force and a time, I'm thinking impulse. So let's write down some givens. We've got a VI of 100 kilometers per hour, which is 27.77 meters per second. VF is 0 because it stops. My mass is 62 kilograms. My time is 90 milliseconds, or 90 times 10 to the minus 3 seconds, or you could say 0.09 seconds. What's the force? I'm probably going to say delta P is equal to F times T equals M times delta V. And I'm going to use these 2 parts of it, I think. So F becomes equal to M delta V over delta T. 62 times 0 minus 27.77 over 90 times 10 to the minus 3. And I can't remember what the answer was for that. Anybody have it? Do that, we get negative 1.9 times 10 to the 4 newtons. But notice they're only asking me for the magnitude of the force. The direction is opposite to the velocity, but they don't need the direction. They're only asking for the magnitude. Good? All right, let's try one more multiple choice question, and then we'll move on and do a tiny bit of new stuff here today. This one's number 5. This one's also, I believe, on page 11 of your worksheet booklet. Have a look at that one again, about 1 minute, and then we'll take a look at it as a group. Hey, anything stand out to you in this question as you're reading it? I know that you've read it about 2 or 3 minutes ago, but as you were reading it, did anything stand out as being maybe worthy of circling with a red pen or highlighting with a purple highlighter? Or what about the mass of the arrow? Good. Circle the grams. Okay. I'm not worried what the number is right now. I'm just worried about the fact that it's in grams and I might forget to convert that to kilograms. Anything else? As you're reading it, honestly, I mean, after the fact, you're going to realize that this number isn't important. But as we're reading it, we don't know that, right? As we're reading it, we notice that that's centimeters, and we don't want to be in centimeters. There's 2 units there, again, that we want to convert if we need to use those numbers. Okay, what's the question here? What's the concept that's involved in this question? What's really going on? This one's more obvious than the other one. I wouldn't say it's easier to solve, but it's more obvious as to what we should do. This question says, what is the impulse? Right, that's the one that the 5-year-old could figure out, right? Not 5-year-old couldn't do the question, but the 5-year-old would know that it was impulse. Let's write down some givens. We got a mass here of 0.0206 kilograms, or you could say 20.6 times 10 to the minus 3. We've got a force here of 130 newtons. We've got a displacement here of 0.70 meters, although it turns out we're not going to need that. We've got a VF of 94 meters per second. That's how fast the arrow is moving when it's released. We want to find impulse, delta P. I'm going to say F times T equals M times delta V. Solving for impulse, I got mass, pretty much have delta V, so let's go with that. M is 0.0206 times VF, 94, oh wait, what's VI? Yeah, 0, good. 0, we didn't write that down as a given, but it is 0 meters per second. Now, it's important that we recognize that that's delta V. In this question, if you just said V and made it 94, you get away with it. But if VI is not 0, then obviously if you forget to include the VI, you're going to make a mistake. 0.0206 times 94 ends up being equal to 94. And that would be 1.94 Newton seconds, or you could say 1.94 kilogram meter per second. It would be the same thing. We'd record that on our answer sheet as 1.94 like that. Good? We've just gone through a couple of multiple choice questions that illustrate for us some of the quantitative questions that we can see involving impulse, much like the questions that we did on our worksheet and in our practice problems out of our textbook. Today I want to focus for the next few minutes on the qualitative implications of impulse. In other words, what are some things out there in the real world that impulse can explain? Not calculate, but explain. Well, the first thing that we talk about is something that we've already talked about a little bit. The situation is what I call a predetermined impulse. Predetermined impulse is a situation, it's a term that I give to a situation in which the object that is moving will experience the same impulse no matter what. In other words, when an object stops, an object that is moving stops, it doesn't matter how it stops, it will experience the same change in momentum. For example, the car going down the road at 110 kilometers per hour, it has a certain amount of momentum. One thing is certain, sometime later on, it will have 0 momentum. The impulse that that car experiences will be the same no matter how that car comes to a stop. A baseball coming towards you, okay? You're going to stop that baseball. Okay, whether you're a batter and you get hit with the baseball in the back or the head, or whether you catch that baseball with a glove, one thing is certain, that baseball is going to stop. The impulse of that baseball is going to be the same no matter how it comes to a stop. When something is stopping, the impulse is predetermined. It will be the same no matter how it stops. Now, the equation that describes impulse, the one that we want to use here, the one that's relevant to this analysis, is delta P is equal to F times delta T. Let's pretend for a second we have a predetermined impulse of 10 Newton seconds, 10 millinewton seconds, 10 whatever. It doesn't matter what the units are. The impulse is 10. The stopping time is 5 seconds. It takes 5 seconds to stop this whatever. What's the force going to be? It's going to be 2, right? 2 times 5 is equal to 10. Let's say we have the same object stopping with the same impulse of 10, but we somehow managed to increase the stopping time. Maybe you're jumping off the desk and you bend your legs now to increase the stopping time. Maybe you're catching the baseball and you cradle the ball a little bit by bringing your hand back. Maybe your head's hitting instead of this head hitting the steering wheel in the crash, it's hitting the airbag in the crash. You're increasing the stop at time, let's say to 10 seconds. What does the force become now? What times 10 is equal to 10? 1. Thank you, Haley. By increasing stopping time, you decrease force. This is the basic principle behind every single impact cushioning device, period. If you're cushioning your hand with a baseball glove, it increases the stopping time of the ball to decrease the force. If you use an airbag to cushion your head, cushion the impact on your head, then it increases the stopping time, decreases the force. If you bend your legs when you jump off the desk, you increase the stopping time to decrease the force. The crumple zone in a car, increase the stopping time, decrease the force. Goalie pads, you hit by a puck, increase stopping time, decrease force. Got it? Now, there are, in some impact cushioning devices, there is another principle at play as well. Things like goalie pads and hockey helmets and football helmets, they not only increase the stopping time to decrease the force, which they do, but they also spread the force out over more area. So you get hit in the head with a puck, it increases the stopping time of the puck, but it also spreads the force out over your entire head as opposed to localizing it in one spot. Does that make sense? That's not the principle that we're concerned with here today, but there is that principle at play as well. The other situation is when we have what I call, and this is, I'm not even sure this is a word, don't think you can legally do this, when you have what I call a non-predetermined impulse. Can you have two hyphens in the same word? Okay, well, there you go. Physics we can too then. This is when the impulse of the object is not predetermined. This is not when we're stopping an object. This is typically when we're starting an object. The golf ball is sitting on the tee. I'm going to hit that golf ball. The impulse of that golf ball is not predetermined, right? Depends upon a couple of factors, how hard that golf ball, how fast that golf ball actually goes off, what its momentum becomes. When we're stopping the golf ball as it's flying through the air, its impulse is predetermined. When we're getting it going, it's not predetermined at all. Typically in this case, what we want to do is increase the impulse. You got a golf ball sitting on the tee, you want to make it go farther, so you got to make it go faster, so you got to give it more impulse. You want a baseball to go over the fence, what do you got to do? You got to give it more velocity, so it goes farther. And to do that, you got to give it more impulse. How do you do that? Typically there, what you want to do is hit it harder, apply more force. What happens when you apply more force? The impulse goes up as a result of that. That makes sense, right? Of course. If you're a baseball player and you want to hit the ball over the fence, the harder your swing, the more likely it is to go over the fence. The impulse is not predetermined. You're making it bigger. What's the other thing you got to do, though? Listen, you can have the strongest person in the world hitting a baseball, and he's not necessarily going to be able to hit it over the fence, right? You got to know how to hit a baseball or how to hit a golf ball. You got to have good form. If you're hitting a golf ball, you don't just stand like this and go whack. Or same with a baseball. It doesn't work, right? You got to have good form. And good form involves in golf and in baseball. Hold on one sec. anything like that involves follow through, right? When you follow through, what are you doing? You're increasing the time of contact between the ball and the club or the ball and the bat. If you increase F, it increases delta P. If you increase time, you also increase delta P. So what do you want to do? You want to hit it harder and you want to hit it longer. You want to be strong and you want to have good form. All right?